Calculus, calculus. We're still going with some more calculus. And now we're looking at the FRQs. We're going to be doing the calculator portion of the calculus FRQs, which means numbers 1 through 3 on your sample packet. Please do remember that this has changed. This has changed. On the current test now, it's only 1 to 2 are calculator based, and 3 through 4, or 3 through 6, pardon me, are non-calculator. So they shifted one of these calculators over. On the current tests. On this sample test, it's not like that, but on the current test, that is the format. So let's start with the first one. Particle is moving along the y-axis with this function, and here's our velocity. Part A is going to ask us about velocity, speed, and acceleration. Remember that velocity is just v of t. Speed is the absolute value of velocity, and acceleration is v prime of t. So that's how we're going to look at those. In the viewing window, we're going to sketch this. Over the interval, we're going to be asking, is the velocity increasing or decreasing? That's just asking about slope. Is slope positive or is it negative? And then on the last one, find the distance the particle travels. And distance is just the integral from A to B of speed. We have to take the absolute value of velocity because if we're talking about distance traveled, let's say I went 7 units up and then 2 units back. I didn't travel 5, I actually traveled 9. I have to add them together. So even though this is 2 units negative, we got to do the absolute value of it. Okay, so now let's go ahead and get started. That's kind of a plan. Some of you might be able to stop the video and do it from here, but let's go ahead and see what we can do as a group. So we got t minus 4 to the 4th power times sine of t minus 4. So velocity equals t minus something. What was it? 4 to the 4th times sine of t minus 4. So if I want to find that at t equals 3, that means v of 3 is very easy. All I got to do is substitute 3 minus 4 to the 4th power times sine of 3 minus 4. Now technically I can stop there. I don't need to simplify. Why? Because this is an FRQ. Say it with me. It's an FRQ. Therefore I do not need to simplify. But if I wanted to, just for fun. This is negative 1. Negative 1 to the 4th power is 1. Sine of 3 minus 4 is going to be times sine of negative 1. So that's my velocity at 3. Let's look at the other two. Speed is going to be pretty easy. That's the absolute value of velocity. So that's going to be equal to the absolute value of sine of negative 1. And no, I don't need to plug that in and simplify it. Why? Because it's an FRQ. I don't actually have to find the approximation unless I need to use it for something else. And right now I don't. Acceleration. Acceleration is equal to v prime of t. V prime of 3 is going to be the derivative of this. So I need to take the derivative. I need to figure out what that is. So let's go ahead and do that first. Derivative v prime of t. This is going to be a product slash chain rule. Here's u, here's v. So we're going to do product to chain rule. Let's color code this. We'll do the u in red and the v in purple. Sounds good. So we got u prime v. So that's u. It's going to be v of t, v prime of t is equal to t minus 4 to the 4th times u prime v plus v prime u. Actually, we need to take the derivative of that. We could do it either way because it's product rule, and product rule works both ways. But this will be 4 times t minus 4 to the 3rd times the derivative of the inside, which is just 1. Because the derivative of t is 1, and derivative of negative 4 is 0. So I don't need the 0, I just need the 1. So it's u prime, that's u prime. Then we're going to multiply that by v. V in this case is sine of t minus 4. Plus v prime u. So now we need to do v prime, if I can write that correctly. V prime is going to be cosine of t minus 4 times 1. How do I know that? It's a chain rule. Derivative of the outside of sine is cosine. Leave the inside alone, then multiply by the inside. Okay, and then we're going to multiply that by the original u. which is t minus 4 to the fourth. When I'm trying to find v prime of t, or the acceleration when time equals 3, all I got to do is plug this in. So it's going to be 4 times 3 minus 4 is negative 1 to the third times sine of negative 1 plus, now I got this other stuff here, 3 minus 4 is negative 1, so it's going to be negative 1 to the fourth times cosine of negative 1. Do I need to simplify that? No, I do not. If I wanted to, I don't need to, but if I wanted to, just for plugging it in later, which we might do, negative 1 to the third is negative 1 times 4 is going to be 4, so I got 4 sine of negative 1 plus negative 1 to the fourth is just 1, and cosine negative 1 is just cosine negative 1. Interesting fact here, because sine is odd and cosine is even, this might be written as negative 4 sine of 1, and this might be just cosine of 1. It would be equal to this as well. That's because of the odd and even relationship of the graphs. Whenever you have an odd and even relationship, if something's odd, that means the left side is the opposite sign of the right side, so that means f of negative x. If we're on the left side, that's going to be the opposite sign of just f of x. But if it's even, that means both sides have the same sign. So that means that f of negative x, if that's positive, then that's the same over here, positive f of x. And negative f of negative x is going to be negative f of x. So here we got opposite signs. Here we have same signs. So that's what's going on there. Sine is odd, cosine's even. Would we need to know that? But for a multiple choice question, that might be something we would find. All right, part B, graph v of t. Well, trusty graphing calculator, here we come. Go to y equals, let's start a new one. That means that we're going to have a, what do we have here? We got t minus 4, t, or in this case x, minus 4 to the fourth power. And that's times sine of x minus 4. Do we have an interval? I don't know if we do. That needs to be a 4. There we go. Let's see what's happening here. This is what I just typed in. Close that off. I don't think I really needed this one. I had to go all the way back. Oh, we'll leave it alone. We don't need it, but it's okay. We can graph this. Whoa, so we got a lot of stuff going on. It looks like it goes way up and then way down, and we're looking probably at this interval on the inside. Let's double check that. If we have an interval that we're looking at. Oh, we're going from 3 to 5, and negative 1 to 1. So let's fix that in our viewing window. So for my viewing window, my x's are from 3 to 5, and my y's are going to be negative 1 to 1. Now let's graph it. So that's what our picture should look like. Aha. So let's go ahead and do that. That means we're coming up, flattening out, and going back up. Easy enough? Oh, we need to draw that in this other part here. So it's going up, and then back up like that. Close enough. Part C. In the interval 3 to 5, is the velocity increasing or decreasing? Use your graph to justify your answer. This is kind of a weird trick question because it's asking us, is the velocity increasing or decreasing? So it's saying, is the slope of v of t increasing or decreasing? That's not saying, is the slope of s of t, or in other words, x of t, the position. It's not this. Because velocity does tell us about the slope of the position, but right now we're looking at the slope of v of t because it's asking us, is velocity increasing or decreasing? That one way to think of that is acceleration, or is a of t positive or negative? Well, we can actually just look at the graph. We have it here. Is this a positive or negative slope? It's positive. Therefore, it's increasing. It started low, it went high. It's that easy. It's increasing. So what I could say then is v of t is increasing because the slope, which in calculus would be v prime of t, is greater than 0 over the interval 3 is less than or equal to t is less than or equal to 5. Boom. Done. Next. Find the distance the particle travels from t equals 3 to t equals 5. Show how you arrived at your answer. Now here's something that's kind of interesting. When we're talking about distance, distance is all travel. It's not the sum of the positives minus the negatives. So actually I kind of said that backwards. It's not the sum of the positives and negatives. It's all travel, whether you're going forwards or backwards. So then we need to do an absolute value. We're going to go from A to B of the absolute value of v of t, dt. And that's going to equal our distance. And we know A and B. They're telling us it's from 3 to 5. And then we're going to do the absolute value of v of t. And we can actually do this in our calculator. So let's do that. Let's use our calculator. So I'm going to change this function slightly. I'm going to insert something here at the very beginning. Second, insert the button above delete. Now what I want to do is an absolute value. Absolute value is a math function, so I'm going to go to the math menu, and I think it's in here somewhere. Let's see if we can find it. There it is, under num. So what I did is I went to math and then clicked to the right num, and if you want to see what I pressed, here it is. I clicked math, then to the right, then I went left, then right, which puts me right here. And that's the one that I want. I want absolute value of what I had typed in originally. So now I'm going to go down here and close it off. Now I have absolute value. What this should do is take that negative piece and it's going to flip it up here. So it was down here. We had a negative piece down here, but now it's up here. That's what absolute value does. It makes negative positive. So now I take the integral of this. So I need to do second, calculate, integral, which is 7. Now I'm going to integrate that from 3 is my left bound, is my upper bound, and bam, calculators rock, because my distance traveled is 0.29, whatever units we're looking at. 0.29. Well, let's look back at the units that we originally started with. Particles moving along the x-axis, so its velocity is given by, we don't have any units. They didn't give us units. Normally they do, because you need to add the units here. So in part D, it's 0.29 units. We'll make up our own unit. We'll call it unit. Number 2. Ooh, this one's interesting. Because we have something being poured into a bin, then we have something removed from a bin. This is where we have a net change. So we got to focus on what's happening and then figure out the net change when it asks for it, figure out the positive change when it asks for it, the negative change, and kind of do the appropriate calculation for what the question is. So first thing I want to do is I want to copy these pieces here, the question, because I'm probably going to need to use it again. So let's erase this. I'm going to make a copy of this piece. Alright, here we go. Clipboard. So now I'm going to paste it here so we can look at the function that we need. We know that S of t is this and R of t is this. S of t is going in, this is the in, and this is the out. It says how much sand is put into the bin during the workday. Now remember in the workday it said from 0 is less than t to 9. I don't know if it had less than or equal to, but it doesn't really matter. It probably did. But we're going from 0 to 9 hours. So that means we're going to do the integral from 0 to 9 of S of t, because that's what's being added. That's what's being put in. We're not really looking at the R of t yet. So it's not there yet. It is happening, but we don't care because that's not what the question is. It says how much sand is put into the bin. So if I want to integrate this, I need to use my calculator just because it's so much easier. 5,000 divided by t cubed plus 50. So we got 5,000. 1, 2, 3, 4, 5,000. Divided by. Now here's something that a lot of people miss. You got to put that whole denominator in parentheses. Let me go ahead and delete all these. The whole denominator, and it was t cubed, so I'm going to use x cubed plus, I want to say it was 50. I'm going to type it and then check it. Let's see if we can gamble here for a second. Now if you don't put this parenthesis here on the first half, then it's going to look like something different. It would just do 5,000 divided by x cubed and then add 50 after that. So we got to follow the appropriate order of operations in here. It was plus 50, so let's integrate that. First we got to graph it from 0 to 9. That's our range that we're looking at, 0 to 9. If it's not in the appropriate range, it won't calculate the area for you. It doesn't really matter how high or low it is, but I know that this is probably going to go really high. Let's say we're going from 0 to about 5,000. Something tells me that's about how high we're going to do. For the x scale, I'm going to do it in scale of 1,000, just so we don't have dots all over the place. So I'm graphing it. This is 1,000, 2,000, 3,000, 4,000, 5,000 up at the top. Wow, so it's not really that big at all. Let's go from 0 to 100 then for the y value, just to see what's going on. 0 to like 100, and we'll do it in intervals of 10. Oh, that's much better. So it looks like 100 is more our top limit. So this is how much sand is put into it. Notice that it does slow down eventually. This is kind of a negative logistic growth here, actually. So let's see what would happen if we integrate this. So we're going to second calculate. Integrate is number 7. Our lower limit's 0. Our upper limit is 9. We type those in. Shades it in. The value that we get is 415.4209. Remember, 4 digits is always safer than 3. Oh, I forgot what it was. It was 415.4209. 415.4209. And that is equal to, well, if it's doing cubic meters per hour and we take the integral, then this is just meters cubed. All right, let's do part B. Find S of 6 minus R of 6. Include units of measure. Explain what this number means in the context of the problem. Well, S of 6 is going to be whatever that original function is. S of t is the rate. So it's the rate right now. So right now, S of 6 is the rate going in. And R of 6 is the rate going out. So S of 6 minus R of 6 is the net rate. It's the overall change that's happening. It's the instantaneous rate. It's the instant rate at t equals 6. Now you're probably wondering, wait, how can we find an instant rate when we didn't find the derivative? Well, they gave us the derivative by giving us the rates. So that means if I find S of 6 minus R of 6, well, I got to plug in 6 into each of those. Excuse me. So what I'm going to do then, so I'm going to evaluate this at 6. So I want to just trace it. I want to trace the graph. But for my x value, I'm going to type in 6. Let's see what I get. Y equals 18.7969. So S of 6 equals 18.7969 meters cubed per hour. R of 6 equals, so we got to figure out R of 6. And to do that, we need to actually plug in R. So let's plug in R right here. R of 6, that function, I need to go back and check what it is real quick, is, it's Kind of hard to see it there. Let's erase that. 23.967 square root of t. So we had 23.967 square root of t. So I got to type that into here. So we got 23.967 times the square root, which is second squared, and then t. Well, our variable in this case is x. That's okay. So now we go to the graph. We got a new function here. We want to figure out what t of 6 is. So I want to trace. Is there a way that I can trace the other line? Maybe if I turn this one off. There we go. Let's turn this one off by pressing enter on the equal sign. Then we go to the graph. Okay, now I want to trace this one. So I'm going to trace. I'm going to type in 6 for my x value and see what my y value would be. It would be 58.7069. So this is times square root of 6, which is 58.7069. Sorry about that interruption there. So s of 6 minus r of 6, s of 6 minus r of 6. I didn't even need to actually find that because this is an FRQ, but I just want to give you guys a way to do it in your calculator. Because I could just say this is s of 6, which is 5,000 over, what do we have? 6 cubed plus 50 minus, that's s of 6, r of 6 is 23.967 times the square root of 6. That's the net change. That's the rate, the net rate at t equals 6. All right, let's see if we can wrap this up here. Explain why the maximum amount of sand is in the bin when s of t equals r of t. Well, this is what's happening. So we know that s of t minus r of t is equal to the overall rate. And we're back again. Too many interruptions. Alright, so s of t minus r of t equals the overall rate. It's the rate of our function. It's the rate of change of sand in the bin. Because it's the net rate. That's how you find that rate. So if I want I know that when my rate of change equals 0 and it's increasing before and decreasing after, and it's 0 in between, that means I'm going to hit a max if it goes from increasing to decreasing. Well, how do I know this? Well, if I look at the two rates, let's go ahead and come back here and look at the two rates. I'm going to turn this first one back on. So now let's look at the graph. Notice that before that point where they equal each other, the increasing one, the positive one is greater and the negative one is less. Another way to look at this graph is, let's say I graph it from negative 100 to 100. So I'm going to do that. So I'm going to type in negative 100 here. And then on the graph, so now as we're graphing this from negative 100 to 100, we can actually look at the net change. So I'm going to take these two functions, the original one, which is the amount going into the bin, and the second one, the amount coming out of the bin. I'm going to subtract them. So I'm going to create a third function that's the difference between those. And thankfully with my calculator, I can do that very easily. So if I go to vars, and then, whoops, that's not what I want, vars, and then yvars, I'm going to click on function. So we want the first one, which is y1. Then we're going to subtract the second one. So I do the same thing, vars, yvars, y2. There we go. So we got y1 minus y2. I'm going to turn off the first two functions here. So that way I'm just seeing just the net change, not the in and the out, but just the overall. So now when I go to my graph, I notice that here it's positive before, the net change is positive before, it's negative after, it's 0 in between. So right here it's 0 in between, and here it's positive, and here it's negative. Alright, let's get back on track here. Too many interruptions. Time keeps passing, keeps changing, but we need to get back on track. So the overall rate is the rate of change in the sand bin, and when we look at the graph of what's going on, we notice that it was positive before, positive up here, negative down here because it's above the x-axis, then it goes below the x-axis. That means we're hitting a maximum amount here. That's why. So, explain why the maximum amount of sand has been when S of t equals R of t, because S of t is greater than 0, R of t is less than 0 before S of t equals R of t, and then after those two kind of flip-flop. The S of t, actually I shouldn't say this. Let's put these two together. So S of t minus R of t is greater than 0 before, and then after S of t minus R of t is less than after. It's positive before, negative after, therefore it is a maximum. I didn't write that out in formal sentences, and you guys should, but I'm just trying to give you the idea of how to interpret it. How much sand is in the bin at the end of the workday? Well, that means that's going to be our total in minus our total out. There's one minor detail to watch for here. It's being put in from 0 to 9, and the accumulated amount going in is S of t from 0 to 9. And then the total out is going to be from 1 to 9. So we know that that's only happening from 1 to 9. So then what we need to do is subtract these. So I can do each of these separate, which is what I'm going to do. And we actually already figured this one out. We figured out the total in. That's from the answer from part A. So I just need to figure out R of t from 1 to 9. So let's use my calculator. We're going to turn off this net change one. We're just going to look at the R of t. So we need to calculate R of t. I'm going to calculate this. Second, calculate. We need to do the integral, which is number 7. Calculate it from 1 to 9. And that becomes 415.428. So this is 415.428. And this original one was, the answer in part A, I believe, 415.4209. $415.4209. Well, then you're probably asking how much sand is in the bin at the end of the workday? Next to nothing. So it's almost nothing because this minus this is practically 0, especially if you were to round it off to the second decimal place. Then we'd have this minus itself. So it's just 0. 0 sand at the end of the workday. Number 3, this is the last one, and then we're done with the with the calculated portions. It is estimated that the current rate of consumption are gallons per year. The oil company, or the oil supply of the earth will last about 200 years. However, the rate of consumption R of t is increasing at a rate of 5% per year right here. So it's asking in terms of how many gallons of oil are currently available. Well, that's saying that if we are losing so much that in 200 years it'll be gone. So we have R gallons per year. So dr dt right now at time equals 0. So now, not 1 year from now, but t equals 0. This equals R. And in 200 years, that'll be gone. So R times 200 is the amount that we'd use in 200 years. So that's how much we have left. We have, right now, the current total is 200 R. Because 200 years times what we have now is all that we have left. So that's part A. I should actually put that on the part A part. So what we have, so the rate times the time equals the total total used up. So the rate right now is R, and the time is 200, and that's our total available. So that means we have 200 R. Let's look at D. It says use the given differential equation to find R of t. Well, it said that R of t, or dr dt, is equal to 0.05 t, I want to say. So what we're looking at then is the original equation. We have dr dt equals 0.05 r. What we need to do in order to calculate this is realize that we can integrate this. But in order to integrate it, we have to separate the variables. So I'm going to bring this r over to the left and bring the dt over to the right. That means I'll have d times capital R, or d capital R over r equals 0.05 dt. Now if I want to calculate this, or if I want to integrate this on both sides, let's do that. So I'm going to integrate. The integral of dr over r is just the natural log of r. And the integral of 0.05 dt, the integral of a constant, is just that times the variable, so it's 0.05 t, of course, plus c. Now I want to do e to both sides. And remember that this constant here is actually going to turn into a coefficient, so it's going to be c times e to the 0.05 t. E to the natural log are inverse operations, so those undo each other. We just have r equals c times e to the 0.05 t. So the only thing that we'd be missing is this constant that we're starting with. Well, that constant is the current amount that we have at t equals 0. Because if I plug in 0 here, r, when t equals 0, is going to be equal to c times e to the 0.05 times 0, which is e to the 0, so that's just 1. So c is our initial value. Well, our initial value, what we have now, is 200r, 200 lowercase r, equals c, not e. I'll do that. Equals c. So r then is 200 times little r times e to the 0.05 t. Let's look at the next one. It's saying if no additional oil is discovered, how long to the nearest year will the current oil supply actually last? Show how you arrived at your solution. So what we're trying to do is we're trying to figure out when does our consumption go to 0. Well, if we want to figure out when our consumption goes to 0, we're actually having a negative growth. So what we need to do is see what happens when our big R, when does big R t equals 0. Well, let's notice something here real quick. It says that it's decreasing. This says 0.05 of r here. So if we were to graph this original equation here, We want to see when does that come down to 0. Well, let's say big R right here was just 1 or something like that. We're trying to figure out when does that go to 0, show how we arrived at our solution. Let's go ahead and graph. We're going to clear these ones from the previous. So we have 200 R, which is the current rate. Now, let me think about this for a second. If t equals 0, R is our current rate, okay. So we're going to have 200 times e, which is second natural log, e to the 0.05 is our variable, which is usually x, even though it says t. This. Now we were looking at up to 200 years, so I need to go somewhere around there. Let's say that we go from 0 to 200, and the y minimum, we don't need to go down, so we just need to see when it equals 0. And the y maximum, sure, we can stay at 100. We have a function that's still not working here. Maybe it's too tall, actually. So let's go to window. We're going to change our y maximum to just 10, 0 to 10. And for the y scale, we can go from 1. And then for the x scale, we can do that by tens also. Do we still see anything? We still don't see anything. So we have 200 times the current rate times e to the 0.05x. So with the graph, we're not getting a lot of information. It's because we don't know what r equals. So we kind of have to do it in terms of r. So let's see what we have. If we have r of t equals 200 r times e to the 0.05 t, we want to figure out when does that equal 0. 0 equals 200 r e to the 0.05 t. Well, looking at this, we can divide both sides by 200r, so that's going to be 0 over 200r equals e to the 0.05 t. And that's just going to be 0, so when does 0 equal e to the 0.05 t? If we were to take the natural log of both sides, that kind of doesn't work too much. So let's go back to the graph and try graphing this one. We can't take the natural log because natural log of 0 does not exist. So we can't really do that. It's a limit. It goes down to negative infinity pretty much. So looking back at our graph, I'm just going to take this 200, delete it off. So when does this equal 0? Actually, that needs to be a negative, because we are going down. But when does this equal 200? Ah, that's what we need to look at. So when does that equal 200? Because that's all that we have left. Well, 200 is just above that graph. So if we change our graphing window from 0 to 300, we're looking at when do these two functions cross? We need to change the window here, it looks like. The x maximum, oh, we didn't need to go to 300 there. We need the y maximum to go to 200. It looks like our x, we can probably go just to about 50. Looks like that's not going to be far enough. Change our x value out to 100. Ooh, it looks like it's only going to last about 100 years. So now we go to, window, we're going to change our X value to go out to about 150. So our two graphs definitely cross right here. So if I want to find the intersection of those two things, I can do second calculate the intersection, which is number 5. First curve, we know it's going to be at about 100, I think. Just past 100 almost. And then the second one, that looks about good. Guess. So it looks at about 105.96635. So T equals 105.96635. What are we looking at then? We're looking at when does R of t not equal 0? Because we know that we have this amount to start with here. That's how much we actually have. It's kind of our initial value. We're looking at when it equals about 200. Because when R of t equals 200, that means that our use, we've used up. This is what we've used up. Used oil. Our used oil equals 200. That means we've used up all the pieces that we have. All the oil that we have. And that's it for this.